Hello, my friends. I'm online today a little bit earlier and for, I hope, a longer period of time. The project is big, there is a lot of work, and I realized that working on it once a week for an hour or an hour and a half is not enough, so I need to speed up the work. Not speed up the work more. So hopefully today I will work more, speak less, and move the progress forward more than last time and the week before. So let's start. Compute module 4S carrier. 4S means generation 4S, SODIMM size, SODIMM module. We have schematic that contains the boot USB. There are two USB-A's connected to the Ethernet thing that converts, or not converts, it's, I can say it's a bridge between USB and Ethernet, 100 megabit Ethernet, and on the downstream of this IC there are two USB-A's, standard USB, not USB-A's, standard USB 2.0s, and these two zeros will be connected to the regular USB-A's. There are HDMI output. There is a HDMI output with eFuse. There is micro SD card. Despite the fact that this 4S module, not this, there are 4S modules that are called light. These modules don't contain the eMMC memory, and then these modules need to boot from SD card. So there is a micro SD card slot connector. My 4S module that will be used does contain the eMMC module, but never mind, there must be micro SD to be the carrier must be universal for all possible 4S modules. The compatibility thing, I didn't mention it. I haven't mentioned it because I didn't think about it. I think there will be no backward compatibility. I don't know if there is 3S compute module, probably yes. C, I'm completely uninformed and uneducated. I don't know. We can check it afterwards. The top priority is to create this carrier for 4S. There is no 5S carrier, 5S module, only compute module 5, which is the almost credit card size, smaller than credit card size module. But 4S is SODIMM the most advanced SODIMM module is 4S. GPIOs, we stopped last time when searching for, I was searching for a logic, I can say isolator, but it's not isolator, just buffer, ideally with a voltage translation feature, but at least a bidirectional buffer can be fine. I found a great one, pinout friendly module, but for quite high price. And one of you, I can find the name, but I don't know if it's important right now. One of the watchers of this stream recommended this, and I realized, yes, I have these ones in my library already. I have used them before, despite the fact that the package was slightly different. So I I added another symbol into my library with 𝗜𝗁𝗀𝗶𝗃𝗀𝗃, which is very convenient to solder. The other one is this D with US-on20. This is quite, yeah, the device is the same, but see, there is TSSOP 6.5 times 4.4 millimeter size of the package, and the D1, the SON 20, is 2.4 millimeters, so 2 times narrower and 2/3 of the length as the package SON in comparison to TSSOP. In other words, I will use the PWR package, which is convenient to solder. There is 0.65 millimeter pitch, and that's it. So last time at the end of the show, I assigned all the GPIOs to the header that will be used, which is standard 2-row 2.54 millimeter pitch header, and now I want to isolate all the GPIOs with I don't know, 4 maybe 5 these buffers. I hope it's a good idea. Why I am doing it? Because these GPIOs are, in fact, I don't have, or none of engineers like I am have the full schematic of the compute module 4S, but according to my information gained from the datasheet and available information online on the 𝗞𝗶𝗖.com website, etc., these GPIOs are directly exposed GPIOs of the CPU, so no protection there. And I feel like I can't expose them directly to header because it doesn't work like this. It's too dangerous. So yeah, let's go. I create one block with this device. Let's see the recommended schematic. I hope 2 100 nanofarads decoupling capacitors on each side. Output enable is reference to VCCA. I will verify it right away. Output enable should be tied to ground, so I put on resistor. No. Output enable is active, positive active high, yes. So when, yes, output enable is supplied by VCCA, and to ensure the high impedance state during the power up, output enable should be tied to ground. The thing is that I don't want to dedicate a GPIO to control these output ports. So there can be something like a voltage supervisor sensing the 3.3 level, and when the 3.3 voltage is in the range of the typical operating regime, the output enable will be globally enabled. So tied high. Yeah, I don't want any manual switch. I don't want any. In fact, there can be slider switch because normally. No. This will be unelegant. This will be awful. Yeah. Supervisor. There are some. There is a run signal to reset the Raspberry Pi. I will. Yeah. Please forgive my ADHD-ness. I'm not ADHD, but during each stream I feel like that. I will replace the header with a small switch. Tactile switch. With a ESD protection, of course. ESD. See, I started working on the ports and now I'm tuning the reset button here. Never mind. Okay, here is the LED. When the LED is on, I have to check the run signal. I'm not sure how it works. Run. The pin when high signals that CM4S has started. Driving this pin low resets the module. This should be done with caution. If files on, okay, sure. So when the run is on, this transistor is disconnected, is off, so the LED doesn't light. When the switch is pressed, the transistor is on, is conducting, and the LED blinks shortly. Not blinks, yeah, light up shortly. There is activity. EMC, I will check it later. Yeah. So again, this pin when high signals that the 4S has started. So we can take the run signal to control our buffers, because when the CM4S is running, the output enable can be asserted high. Yes, driving capability of the run signal. I will add some. Internally put to 3.3 via 10K. Okay, I will add a one gate, single gate buffer, because yeah, I don't want to overload this signal. But it means that I need a global label, which in this case will be output and will be used in the GPIO section to control all the output enables. Let's go. So I have to check the data sheet. Port A, maximum voltage on port A is 3.3, while maximum port voltage on port B is 5.5. It means that the B side will be external and the A side will be let's say internal or CPU side. Are there any recommended resistors? No, just the openable, but yeah, I will see depending on the user driver. I want to have these lines of the same length. Yeah, there are only all these ports will be changed to global labels, and these will be changed to or renamed to like GPIO2 external, or something must be changed. Okay. I think there is a regular expression possibility. Okay, let's ask the AI how to do it. Okay. We'll see. I need to create a regular. It's called regular. I'm regular expression. Yes. Expression string. Helping me rename strings with a typical format of GPIO02, GPIO03, GPIO10, GPIO11, etc. I need to add a suffix of underscore ext. The output will be then GPIO2 ext, GPIO3 ext, etc. GPIO10 ext, etc. Okay, search pattern is this, and the replacement string is this. Okay, but I need, let's try the search pattern first. Let's start with selection only. Okay. This is something, and we want to replace it with I don't know if KiCad accepts this. I think not. It's like doesn't work. Yeah, I think the thing is that KiCad uses different notation for the yeah, I need to check regular expressions. Okay, let's search again. No, nothing. Yeah, I don't understand the regexp. Search pattern, GPIO. Matches one or more digits. Okay. And this is end of the string. Okay. So start of the string. Okay. We don't need this. We don't need to mark start and end. No, it doesn't work. I don't know how to make it work. Issues. Okay, I don't know. I will do it manually. Never mind. Output enable will be something like run. Output n. Yeah, this is a block. I need a buffer or inverter. So I need a thing that contains 1G in logic. Yes. Single Schmidt inverter, inverter gate, buffer gate, probably 3-state. Inverter. We need logic high. We need yes, logic. So I have the Schmidt gate. And this is without the Schmidt. Without the Schmidt hysteresis. This is flip-flop. I will use this device. Okay. The package can be larger, but never mind. Not so small. The pin number we have DCK package pin number 1. DCK pin number 1 is not connected. Yes. Input is 2, output is 4, 3 is ground, 5 is power. Yes. So this is our enable buffer. Let's put it here. And because the device is perfectly pinout friendly with the connector, yeah, it's manual work, but I think it will be faster than my research with the regexp in Gemini. I will have to check it later. I think I used it before, but probably I don't know. It's too programmer, and I'm not. Oh, go away. Okay, so we have our labels for the ports. We have to squeeze them into a group of 8, like this. And I will add the hierarchical ones right now. Collect. Not collect. Select them. Change to hierarchical. No, hierarchical global. Yes, and ideally these are bidirectional, but this will need a trick. Okay. Trick that I have to help a little. GPIO will be set to bidirectional, and every other not. And I open these symbols in text editor and look for GPIO2. GPIO2, but pure 2 here, shape bidirectional, and other ones have shape input. So I will look for shape input and rename it to shape bidirectional. So here, edit, replace, shape bidirectional, and here will be shape input 42 times. Okay, all are changed. Copy, paste. Okay, GPIO 8 is missing. Why? GPIO 8 is missing. Why is missing? Is the GPIO 8 somehow special? I'm confused. GPIO 8? No. So here are all ports in incremental order. Okay, 8 is here. I don't know. 2, 3, 4, 17, 27, 22, 10, and 9. It's possible that the order... No, I think the order will work. Yeah, we'll see. So here is our block. Yeah, I need to copy it like this. This will go away. This will continue. And for the sake of simplicity, I will not combine signals from both sides, or I can, in fact, because I can go in the middle of the pins. Yeah, to prevent going from both sides of the GPIO buffer header, because the header will most likely be placed somewhere on the edge of the board. Okay, so okay, let's start again better. So it means that the first will be number 2, second will be number 3, then number 4, then number 14, then nothing, number 15, number 17, number 18, and 27. Then 27, there is nothing, 22, 23, nothing, 24, 10, nothing, 9, 25, 11, and 8. And the third one will be, we have to continue from 8. 8 is the last one. Here is nothing, number 7. Nothing, nothing, 5. Nothing, 6. 12. 13. Nothing, 19. 16, 26, and we need one extra, which is unwanted, but what can I say? 20 and 21. We can distribute the signals among the 4 buffers, like there are more than 2 on the fourth one. But yeah, so far it's like this. 14, 15, 17, 14, 15, yeah, 17, 18, 27, 22, 23, 24, 10.9.25. $11.8. Seven, 5, 6, 12, 13, 19, 16, 26. Oh, there are more ports than on the header. Okay. I didn't know that. I thought that all the ports are exposed. That's not the case. Okay. Okay, so let's use only the used ones. Okay. ID SD, ID SC. I should have placed them. I can see now. Because hey, how it's called? How SD. What's this? What not? Oh, I see. These signals are only on the header, not on the Raspberry Pi. Okay. ID SD pins. These pins are reserved for head ID EPROM. These are connected. Okay, I won't use them. So these won't be used. 28 to 45. Frankly, I'm surprised. Okay. Okay. Okay, test points only. Test points only because, yeah, based on my experience, whenever you say that you won't need anything immediately when you're testing the board, you find out that you need it immediately because you make a mistake, and then you need exactly that unpopulated and unconnected port every time. No tak. Okay. The names. Okay, I have to do it manually. Because there is no... Okay. Well, at least... Okay. SDA0, SCL0, GPIO. SDA0. Okay. Where was the table with all the signals? Here. Yeah, SDA, SCL. Yeah, we need it. Why they didn't expose the SCL and SDA zeros? I don't know. I don't know. So I will place test points instead. So GPIOs. Here is the header. Here are 4 buffers. I will keep them as they are. And here is the buffer for the output enable. It means there is the direct yes logic. When the run is high, the output enable is high. It means when the Raspberry Pi is running, the output enable is enabled, is asserted high, and this is enabled. Here is the push-pull output, so we don't need pull-up register because the ports will be always on defined level. Okay. I will not place the ESD diodes. No, it will be too complicated and I don't want to overcomplicate this. If you want, add it. I don't. It would be nice. USD protection. There are some diodes. Okay, let's call it done. Relay 1 should be connected somewhere. Here should be some terminals for it. So relay number 1 or relay 1, GPIO 80, no. You will be GPIO 28 because wait, 28 is fine. One enable will be 29. This can go away. EMC disable. Let's check what does it mean. EMC disable negative. EMMC disable. This pin, when low, signals to the CPU that boot should not occur from either an SD card or eMMC, forcing USB boot. This pin is internally pulled to 3.3. Okay, so this is input to the CPU. Yeah, in the form of the drain of this switch, and we need this signal again as well. This pin is driven low to signal that the CPU wishes to access the SD card. I'm not clever from it. Yeah, eMMC enable. It means that the CPU wants to access the memory devices, so it ties low the enable. Okay. So this switch is active when the CPU doesn't want to access the CPU devices, so it's not booting. Okay, so the signal is active when the CPU is not booting, and when you connect jumper here, I can replace it with the switch again with USB boot bus or 5 volt or 3.3 volt. It means that the ESD disable is tied low. Jumper is fine because the process will take some time. I'm thinking about USB boot bus. Is it a correct signal for it? I think I will do this. Not this. This must be a little bit more complicated. The boot bus signal means that there is a connected computer to the boot port. So you need to first connect the computer, then okay, that can work. Yeah, connect the cable, then or yeah, the jumper can be there, then you connect the cable, the signal is active, the switch is on, this is on because the CPU is not booting, and the booting is disabled either from SD or eMMC. Yeah. Okay, that can work. These are in bold. I will keep it. Who cares? Here is the battery. Yeah. I think we are good. 𝗞𝗶𝗖4S, is it? Yes, we are feature complete. I will take a 1 minute break. Let me say something. If you like what I am doing, I recommend checking this course. This course is a tutorial on 𝗜𝗶𝗖𝗱 platform. You can learn with me how to design this small industrial board with Raspberry Pi dual-core RP2350, M2 connector for this is Node card modules, SD card slot, 2 USB-As, 2 power supplies, 4 analog inputs, 4 power outputs, a bunch of other things, LEDs, buttons, everything is there. So check it if you want. I will be here. I will be back in a minute. Okay, I am back. Let's continue. Let's annotate the entire thing. The thing is that there are some there is something previously done, but I don't want to continue. I want to start over. So okay, the best way how to start over is this. Fresh. Yeah. We want to. We are not finished yet with the schematic. There is the relay. We need to assign a terminal. Here is 5 volt level. 5 volt we have from the power delivery, yes, and 3.3 from the buck, yes. So we need terminal or terminals. Something small. Maybe slightly bigger, because there can be 230 volts. Like terminal block that can be pushed in or pluggable, or I don't know how it's the official way. Can be the thing, yeah. The big one. Yeah. So this is relay 1, normally open. This is relay 1 COM, not CON but COM, and here is normally closed. Yes. And I think we will see. I will start with this setup. Normally, oh, I didn't want to move it away. COM is here. Here will be not connected, normally connected on the bottom. Yes, and normally open on the top. Like this. We don't need to overcomplicate things with, I don't know, with varistors, TVS and something. No, we don't need it. Relay 1. Relay 1, okay. GPIOs are done. Relay is done. Power, let's see, probably done. HDMI is done. USBs are done multiple times. SD card, okay, looks good. Ethernet, yeah, 2 USB ports, a prom, yeah, should be done, and the core. Reset, boot, battery. All ports are assigned or set as not connected. Displays, we don't need it. Cameras, we don't need it. This is, I don't know for what, we don't need it. Test points on the ports and yes. SD card interface, USB, okay. Yeah, I will annotate the entire thing to have Why? Entire schematic, clear annotation, close. Yeah. Why the hell USB started at 15? Entire schematic. No, I don't see. The KiCad probably starts with the sheet number 1, not with the graphical representation of the sheet number 1. So it means that this is U1. Yes, okay, never mind. Fine. So, ERC, where will be something? Yes, let's start with the errors. Yeah. Okay, some warnings. Okay. 3.31. This is not 3.31, this is 3.3. Okay, let's start. Earth is not driven. Yeah, it is. It is not, because it's a formal chassis connection. I can assign the power flag, but in fact, it's not power flag. In fact, this is just a symbol. V-bus. Okay. Power flag. Let's copy it because we will need it multiple times again. Battery, okay. Battery is, I screwed the grid here. So here, here is power, here is power, here is power, here is power. What's this? Here is power. Oh. Hidden pin number 4. Power output. That's probably SDX VDD pin number 4. Pin number 4, SD card supply. SD card supply. The same as pin number 6. Why is it? There's something wrong in my symbol. Pin number 4. Pin number 6. Okay, I need to check the symbol. Here is pin number 6. So it means that pin number 4 and pin number 6 are identical. Should be here. Set as passive. Okay. So ground TMC disable GPIO 0, SDX GPIO 1, SDX pin number 7 ground, 8 ground 2, SDX clock 3, SDX command ground 4, D0 GPIO 5, D1 ground 6. Okay. 6. X2 7, D3 ground 8 28 9 29. Ground 10 30 11 31 ground. Negative write protection VDD for first of 28 ports, VDD 28 ports. The rest ground 12 32 13 33 ground 14 34 15 35 35 ground 16 36 17 37 ground 18 38 19 39 ground 20 40 21st 41 ground 22 42 23 43 ground 24 44 25 45 ground 26 HPD N 27 enable N ground the N1 DP0 DP1 DN0 ground DN0 CP DP0 CN ground CN DP3 CP DN3 ground clock negative DP2 clock positive DN2 ground DO0 DO9 DO negative DP1 DOP DN1 ground HDMI 1 D1N. Okay, not connected. 23 yes, 24 no 24 not connected. D1P 25 not connected. Ground D2N not connected. D2P not connected. Ground DP3 DP0 and 3, okay. Here, D and 0, ground, ground, DP2, CP, D and 2, C and ground, ground, CP, DP1, C and D and 1, ground, ground, DP1, not connected, D and 1, not connected, ground, ground, DP0, not connected, D and 0, not connected, ground. 164, yeah, is ground, DP, USB DP TV, DAC, DM, OTG IG, ground, ground, CEC, TRST, SDA, TDI, SCL, TMS, run, TDO, VDD core, VCTCK, ground, ground, not connected, 187, first ground, ground, DAC, DAC, 4 times 3.3, 185, ground, ground, 4 times battery, and we are done. Okay, the symbol is now correct. So I only need to update everything to be sure. Yes. ERC again. Yeah. Power, and now the warnings. Label run. Yeah, that's fine. Not connected. Okay, OTG IGE not connected. OTG IGE. OTG IGE. OTG IGE. OTG IGE. Do I need to connect it somewhere? ID, no IG. If you're using either SIF fixed slave or fixed master, please tie the USB pin to ground. Okay. Okay. Yeah, they are connected together. That's the thing. That's the thing, that all the not connected signals must not be stacked, because otherwise they are formally connected. It's it sounds ridiculous, but it's the case. Okay, I was off grid when I draw this. Nice. Yeah, and the CPU. Yeah, that's fine. Okay, so ERC is fine. And we can start placing components. Not so crazy, right? Just a few components. So let's group them. Two USB A's. Here is the boot port. Here is the USB, how to call it, multiplexer. So somewhere near the USB and the CM4S connector. Okay, so these will be done later. Here is the HDMI. It's already grouped because it has its own block. SD card the same. I want to be sure. Now, power. I have to split, or I want to split the power delivery part, which is here. This is the power delivery port, so another USB. And the buck converter. The buck converter can be moved closer to the CM4. GPIOs. Okay, so I separate the buffers and translators. And the header. Yeah, the header is just a header. I don't need to move it away. Relay. Here is the relay with its terminal. So can be placed somewhere near the header. Now the GPIO, I'm sorry, the RPI. Here are two more test points along with the other ones. So the test points all the decoupling and power things. Oh, I don't want to here. Here is the power supply. This is the entire connector thing. Here are the reset and boot options, boot setup, boot configuration. Can be, I don't know, over here. Ethernet. We have E fuses for the USBs, so I will move them closer to the USBs, closer to here. We have everything connected with the Ethernet is here, just the IC, I mean. And here is the Mac jack and its components. Okay. What else? Of course, we have a logo, we have a relay with the header, yes, we have battery, okay. And what this? Yes, this is the HDMI, I think, again, as well. Here. And probably here is, yes, the OTG ID and the battery, okay. This somewhere. Nice. So, what will be the size? What will be the shape? Probably rectangular. I didn't didn't think about the shape or size. I will start probably from top left corner and see how it goes. Okay. I don't know. I don't have an idea about it. Let's play with it a little. Just in the PCB. So here is the connector SODIMM. But I thought I have the right angle one, not this one. This one is fine when the I think I planned to use this one because the right angle. Yeah, this is right angle. Not this is straight or right angle. Straight connector. I wanted to use this one because I wanted to embed everything into the DIN enclosure, and there were a lot of space, like height. Okay, let's change it. Let's check the distributors. Yeah, this is. Yeah, and I have to replace it anyway because it's obsolete. Yeah. This one looks good. It's a standard 5.2 millimeter height. This one is higher, but we don't need to place anything below, so. Or do we? No, I do. No. As I can see, the standard is 5.2. Yeah, majority of them 5.2. So let's use the standard one. Yeah. Okay. Yeah. This is not the data sheet I would expect. So we have to visit the manufacturer's website. Yeah, here is the model. Footprint. Symbol, we have symbol. Okay. I think it won't work. Yeah. No. This is not what I want. This is what I want. 3D model. Footprint. The symbol is not needed, so I will step 3D models. SODIM something. Here is footprint. So yeah. There is a thing. Is this connector straight or right angle? I think it's right angle. Mounting feature top. I don't know if it's probably this one is straight because the normal mounting pane is I don't know. Right angle module. So this is right angle, okay. CD PDF, product specification. I have drawing. I need drawing. Yes. This is drawing. But yeah, I don't need it. Okay, I understand. So this will be the name of our footprint. This will be straight. This is straight. Yeah. And we have to copy it and save as. Right angle. This will be our name. Yes. And footprint. No, this. Yeah, be careful. The name. The name is, I don't know, this. The name will be this, yes. We need to add this into fabrication layer. 1473. Fabrication layer, text, reference, here. No leading zeros. This is something. Yeah, I think. Yeah, no leading zeros. Fine. 3D model. So let's prepare for a crash. SODIM, it's called SODIM, this one. No. Here. Save. Crash. Bye-bye. Yeah, I know. Okay. Yeah, this is our new I will use the, it's crazy expensive, 2 times more expensive. I don't know, the search doesn't work on JLC PCB parts. I don't know if it's the same. Probably yes. Okay, we have our new SODIMM connector. HDMI. Basically, the top row is the odd numbers. It means from the first pin number 1, GPIOs, HDMI, basically nothing, HDMI, and probably some power inputs. And the other row, yeah, from pin number 2, SD card connector, HDMI, GPIOs, some GPIOs, yes, GPIOs, basically nothing in the middle, and power entry probably on the right, on the left side. So my idea is to connect SD card somewhere here, HDMI somewhere here, to place power and USBs somewhere here, and Ethernet to be facing the side of the HDMI, and I don't know. Let's see how some commercial products look like. Mm-hmm. Yeah, quite similar to our case. Yeah, that was my idea. To place the HDMIs and USBs and SD card on the top. They have SD card on the right side, but never mind. It's a different module, yeah. Mm-hmm. Yeah. Yeah, we need to. We need to. Do we? Yeah, we need mounting holes, 2 mounting holes. Okay. Yeah. USBs, SD card. Okay. Okay. Here is the nice one. Yeah. Something like this. Exactly. This is what I want. Yeah. Yes. This is what I want. So we set HDMI, that's here. This is micro SD card. This is micro. Looks huge. Micro SD connector, okay, reverse. Okay. Looks huge. Yeah, basically the unused ports are here. Yeah, of course, the header makes all things complicated. Yeah. Basically, everything from top row. Thank you, Leonel. Thank you for watching. Where to place the header? We need one more thing. We need 3D model of the SD card. Compute model, of course, not SD card. For S. There is only data sheet, okay. So, just a regular SOD module. Not the slot module. It's very simple, but frankly, do we need more? Okay. I will use this one. No, just the file. It's rather ugly, but I don't know how deep. Probably it should be in the drawing. Did I already? Most. This is, yes, this is our module. I don't know where. Where is the. Yeah, some probably like this. But I need to okay. I just want to mark the location. Where is the edge of the board? Just ballpark. Yes. And the header can be, for instance, here. Yeah, I stopped speaking because I'm busy placing components now. I want to place the compute module mounting holes and the PCB mounting holes. 2.5 millimeter for the SODIMM. .7, I think, yeah. 2.7, just the holes, probably just the holes. Yeah, I don't know. This is quite small. This is too small. 2.6. I said 2.5. Oh, 2.6 can be 2.6. And here standard 3.2 with ground. 𝗲𝗂𝗏 S1. Okay, these two pads. Okay, I know. S1. No, this one. Yes. Yeah, I need to wiggle. There was a drawing of the compute module. Here. .27 from the corner. 3 millimeters from the edge. It means 61.6 in between. This is so stupid. I can't identify where is the edge of the module from this drawing. If it's this line, or what? No. I'm going to change the terminal because it's too big. No. Terminal. I don't know how to place where to place the battery slot. It's too big and I don't know. We are at 105 and 83. Not so big, but I imagined in my head something smaller. I don't know. I will conclude the stream today because it goes nowhere, and I will continue next time. Thank you for being here. It was not so fun today, but yeah, hardware design is not always fun, but almost every time, almost always. Thank you and see you next time.